Swayam Prabha. Digital India. Educated India.
It's a great pleasure to introduce Professor Rupesh Nasre from IIT Madras. He works on a wide variety of range of topics, works on compilers and architecture and programming models. So today he's going to give a talk on parallel graph algorithms. It's going to be a very exciting talk. So there's a request that questions that you want to ask, please hold on to your questions, maybe note down, and you can ask at the end. Okay? So unfortunately, Rupesh couldn't be here. He was planning to, but nevertheless, this is going to be a great session. You can touch with him later also as well, right, Rupesh?
Yes, sure.
Yeah. And so all your questions, just hold on to it. At the end, once he finishes the talk, ask for the mic, and then you can ask your questions, right? Okay, over to you, Rupesh.
Yeah, thanks a lot, Preeti. I hope people are able to see these slides.
Yes.
Are the slides? Yeah, okay, thanks. Okay, so my apologies first of all that I could not come in person, although I was planning to. I booked the tickets, but for some reason my flight got delayed, was rescheduled, and I was reaching Kanpur late in the, or early morning, I would say. Therefore, Preeti and Ashish sir kindly agreed that I could give this talk on Skype. So please hold on to it, but I'm sure we'll have some interesting discussions along the way. So let me introduce with the graph algorithms, and so I belong to this lab called Programming Languages Architecture and Compilers Education Laboratory, and there are a lot of interesting work that we have been trying to do. And I'm thankful to both Preeti and Ashish sir for allowing me to be part of this HPC Winter School. Okay, so let's start with graphs. So graph looks like this, and where do we encounter graphs? If I would have been physically present there, I would have asked you where do you see graphs, but since I'm remotely looking at this, I'll just say that we encounter graphs not always in the physical form, sometimes in a less natural form. For example, social networks, of course, road connections, for example, one city connected to the another, or one junction connected to the another, molecular simulations, planetary forces, these all lead to different relationships across various entities. And these relationships essentially give rise to graphs. And then there are large variety of graphs. Some could be undirected, directed, weighted, unweighted. Some could have cycles, some may not. Some are hierarchies, etc. So there are different properties of those graphs, but by and large, we are talking about arbitrary graphs here. When we are talking about graphs, I would, those of you who are planning to probably work with some high-performance computing related to graphs, it is useful to know that there are many real-world graphs which are available online, and you might want to download those from, let's say, Snap or Florida Root Networks, Dynamax Challenges, Connect Graphs, etc. So those are all available in different varieties and sizes, so you should definitely try those out. The question that comes up is, why do we treat them separately? In the sense that, why can't we just treat them as matrices or something like that? The important aspect about graphs is that they provide structural information that is embodied inside the application. And once we have this structural information, we might be able to exploit that information, identify certain structural properties of these graphs to process them in a better manner, which essentially means that we might be able to devise better algorithms for solving problems. In general, there are a lot of challenges that graph algorithms pose compared to the counterparts, let's say, related to linear algebraic formulations. For example, there could be load imbalance across different threads when they are operating on different parts of the graph. A typical way in which you will see graph algorithms being processed in parallel is that threads are assigned to different nodes, as you can see on the slide that there are these different nodes of different colors. A thread might be assigned to different threads might be assigned to different nodes. Thread operates on that vertex. Typically, the processing might involve that a thread operating on a vertex might propagate some information from one node to its neighbors. Now, depending upon the connectivity in the graph, it's possible that one thread might have to do less work compared to some other nodes which have probably large connectivity. And therefore, there is an inherent load imbalance which occurs in this context. There is also poor locality in the sense that if I talk about, let's say, matrix-matrix multiplication, then I precisely know just by looking at the code that if I'm accessing I equal to 0th row or j equal to 0th column, I'll be able to, a compiler will be able to figure out that this is how the elements are getting accessed inside the matrix. However, that is not going to be the case in case of a graph, because the compiler does not even know what the graph we are talking about, because the graph is given as an input to your executable. And therefore, depending upon the connectivity, there is possibility that node 0 might be connected to node 60, which might be connected to node 10,000, and so on. So there is arbitrary connectivity across the graph vertices, and this is unknown at compile time. Therefore, compilers, they have to be sound, they have to be kind of preserving the semantics of the original sequential code, and therefore they kind of fall short in extracting enough parallelism out of this. And this property where compilers are unable to figure out how the access pattern is called as irregularity in applications. So graph algorithms is a good example of irregular algorithms. So as I was mentioning, in general, we do see graphs everywhere, such as social networks. This is a control flow graph, which is derived as a representation of the program. So you have some statements which are bunched together as something called as a basic block. And then from one basic block, you go to the other. There might be a condition, there might be branching, there might be loops, so there might be packages, etc. This leads to a graph representation of the original program. This can be very useful when you want to identify certain properties in, for example, in compilers. As another example, molecular simulations, biological networks, etc., where, let's say, different proteins are represented as vertices, or different enzymes are represented as vertices, and their interactions are modeled as a relationship between them. And therefore, this can also be represented as a graph. And then we can talk about various algorithms, various ways in which biological phenomenon can be modeled as graph algorithms. And as I was mentioning, various road networks such as India or even airline road networks can be represented as graphs. Since we are talking about an HPC workshop and we are talking about graphs, I think scalability is something which you must have heard multiple number of times during this winter school. Sorry, I am in Chennai, where currently summer is going on, and hot summer and hottest summer are going to come later. So, okay, so in case of scalability, I'll just give some brief examples. For example, when we are talking about a social network such as Facebook, we have billions of active users. And to put that in perspective, India's population is less than the number of users on Facebook. And if I have to find out, let's say, some top people in the world in, let's say, in a social network, I might require some sort of algorithm to efficiently find out this information. And that top is application dependent, in the sense I might find out the richest people in the world, or I might find out the people who have largest connectivity in the network, or I might be able to figure out, okay, these are the most crucial people from an advertising perspective. I'm an advertising agency and I want to target a few specific people because I have limited budget, but which people should I target such that the spread of my information, the spread of my advertising is the largest. So such aspects become important when we are dealing with large amount of data. Another way, when I'm trying to model, let's say, galactic simulations or Milky Way, right? So there are large number of stars again, and I'm trying to identify some mathematical formulation such that based on certain criteria, whether there exists a possibility of an, let's say, alien or something in universe. All of this requires modeling multiple, this might look like Star Wars movie, but These are real applications which people use in various application domains. Another aspect is, for example, human brain, where there are billions of neurons, and I want to identify certain patterns in how the neurons are fired, etc., to check what parts of the brain get active, what parts are dormant, etc., to figure out whether I can simulate this activity into a computer. Just to give a small anecdote, if I have to find out the importance of a node, there is an algorithm called betweenness centrality. And if I run it in a sequential manner on even a million node graph, 10 to the power 6 nodes in a graph, that itself can take several weeks on your machine. Right? So this is a good indicator that we would definitely require to reduce certain computations, and our parallel computing HPC, distributed systems, multi-core systems, GPUs, etc. All these come into picture when we are dealing with these large amount of data, and more so in the context of graph algorithms. So how do we really handle these large graphs? There are multiple ways in which that can be handled. For example, you might have learned about MPI in this school. So graph can be partitioned into different parts, and then different parts can be given to different nodes in a cluster, and then exchange or communication across these cluster nodes can help us compute the information that we want. I can also talk about external memory algorithms, wherein the graph is processed sequentially on a single machine or a single node, but the partitions are processed sequentially. Because the graph is large, I might not be able to fit that into memory. So what I'm going to do is to take some small part from disk, load it into memory, process it, and push it back into push the result back into the disk and take the next part and process it. These are called as external memory algorithms, which might be helpful in such a context. I can also talk about compression on graphs. Now, what I mean by that is not only that you are compressing the graph and storing it, let's say, on disk or in memory, but I'm also talking about that you are not allowed to uncompress the graph while processing. So you take the graph, compress it, store it into memory, which is limited, and then on this compressed graph you perform the operation. So your compression algorithm needs to be aware what kind of processing is kind of allowed to be done on this compressed data. Right? So this is a challenging problem. Sometimes application-specific compression schemes have also been developed for this. Another more theoretical aspect is we maintain the graph core, which means that for a particular algorithm or for a specific set of algorithms, I'm interested only in certain parts of the graph, which means that I might not be interested in certain specific vertices or certain specific edges, so I need not load them into memory. I can just delete them from the graph and get a smaller core of the graph, which is specific to this set of applications. For example, it might be the case that I'm running, let's say, MST algorithm, and if there is a cycle, the largest weight edge I might be able to remove, right, from a cycle, which is still guaranteed to give you MST without any approximation. So these are different aspects which we need to worry about while handling large graphs, which are related to the storage aspect. When it comes to time, I might as well be able to talk something in parallel, where I can say that in a multi-core distributed or GPUs or a heterogeneous system, I require to process this graph. And another aspect which comes very similar to the compressed data is about the approximations, which mostly we will not be talking about. Okay, so we'll focus more on the parallelism, and we'll also focus more on the GPUs part. Various approaches exist to extract this parallelism out of the graph algorithms. One way is just manual parallelism, which means that I explicitly code that this is the vertex, I do all the malloc allocations, and I specify what the links across different vertices should be, how the parallelism should be encoded, that this particular vertex should be given to these threads, and so on. So I do that manually myself, let's say using P threads or something. So that is an approach which is definitely going to be useful, but also it's going to be a little more challenging with respect to implementation. This is what we'll most probably do when you are dealing with an HPC course and you have assignments in a particular language. The second aspect comes as libraries, which means that there exists some framework which provides a certain library which you can link with. And there are certain classes or certain API which are provided by this library. And your job is to not implement all of this, but just use those library function calls. And that becomes much more productive because these are already optimized for graph processing. The third aspect, which is slightly more higher level, is a domain specific language, which means that you have a language for specifying graph algorithms. The language is providing various constructs for, let's say, processing different neighbors of a particular vertex, or performing BFS on a breadth first search on a graph, and so on. So these are different primitives which are part of the language itself. And when I talk about domain specific language, this means that it can only specify operations from a particular domain. For example, you might not be able to write a primality testing program in a domain specific language for graph algorithms. So there are domain specific languages, DSLs, for this also. And as you would imagine, the productivity goes on increasing as you go from manual to libraries to DSLs, and the performance kind of reduces as you go in this direction, which means that for getting a good abstraction, you might have to pay some penalty in the context of performance. So specifying parallelism, well, to connect to the previous slide, first thing is don't specify, which means that the automated compiler tries to identify, the compiler tries to identify in an automated manner whatever is the parallelism opportunity available. This is possible for nice matrix-based algorithms where the access patterns are determinable at compile time, but not always specifically for irregular applications such as graph algorithms. Another way is implicitly specifying parallelism. For example, I can talk about aggregates, aggregate functions, which are internally parallelized. A library-based approach fits well into this. And similarly, the third one is explicit parallelism, where I myself code up exactly what I need to do. So pthreads, MPI, CUDA, these all are explicitly parallel implementations. When we are dealing with identifying these parallelisms, I'm going to give you a small brief on how that needs to be done, either manually or by an automated manner. So I'll just take a small quick example. For example, if I have a loop, right, and I want to parallelize it, which means that different threads are going to operate on different iterations of this loop. So different threads work with different values of II in this loop. The computation is talking about assigning some value to 2i and reading some value from 2i plus 1. The question here is whether if I execute all these iterations in parallel, whether there exists a dependence across any two iterations. The dependence matters because one is reading a value from the same array and another is reading and writing a value from the same array. So there is a possibility that there might be a flow dependence or a raw dependence or a true dependence, which means that there is a raw meaning read after write. So there is some iteration which is writing to a particular memory location, let's say A of X, and whether another iteration afterwards is reading that value. If that is the case, which happens in the sequential setting, then I am not allowed, or I have to be careful while parallelizing this, giving these two iterations to two different threads. Right? So how do we do that? So one of the ways in which it gets modeled is using a linear set of equations. So I can specify two iterations, let's say IIW, in which the memory location in the array gets written to. So A of 2 IIW is what gets written in some iteration IIW, and there is another iteration IIR in which the reading of that element happens. Right? The constraints on IIW and IIR are that IIW must happen before IIR because we are talking about flow dependence, which is a raw dependence. So the read must happen after the write. And according to the loop iterations, there are constraints that both of these should be between 0 and 9. The other constraint, which happens with respect to whether they are accessing same memory location or not, that happens when the access pattern, which is 2II, for the writing, which is 2IIW, is the same as that for reading, which is 2IIR plus 1. Right? So that is the second constraint. And if I put that into in a less than equal to form, then I get a bunch of equations. I'm sorry, I'll just drink water and come. Yeah. So, sorry about that. All right. So I get a bunch of equations, and those equations I can give it to the off-the-shelf solver, right? So what this solver is going to do is to take these equations and put it in a matrix form, and I can just solve this set of equations. If I solve this, and if the linear solver says that the equations are satisfiable, that is the linear system of inequations is satisfiable, which means that a true dependence exists across these. And if the solver is not able to come up with a satisfying solution in without a timeout, then I can say that no dependence exists across these iterations, and therefore these can be executed in parallel. This turns out to be very useful because then an automated parallelizer will be able to extract this information from the algorithm, from the code, and parallelize it nicely. Unfortunately, this kind of processing is not possible always in the context of graph algorithms, and we'll see a few glimpses of that. I'll skip this parallel architectures because you must have been bored by now about all of this. So I will quickly go to, so in the context of GPUs, although you have looked at it at length in a previous talk, let me brief it for the purpose of this talk. So first thing is that it's a separate piece of hardware, which is typically connected by a bus from the CPU. It has a separate address space, and it allows massive multi-threading, which means that there are a large number of cores which are hierarchically organized, and then there is something called as a warp-based execution, which means that it's a single instruction multiple data format where multiple groups, the groups of threads are executing the same instruction at the same time, or some of them are sitting idle. And if it is difficult for you to imagine what a warp is, I would recommend that you should just go through, think about it as Ravana, where everybody is going to be in sync with whatever is happening, right? So all of these different heads, if they have to, let's say, be in a summer school versus be in, let's say, in a movie hall, these are not possible. However, if they all decide to read books, let's say, they all can read books or watch movies, 10 movies at the same time, right? So this is the notion of a warp. So different threads can operate on different data items, but all of them have to execute the same instruction. Okay, so the computation hierarchy, which starts from a thread at the lowest level, is grouped into these warps, which is typical size is 32. All of these are executing in SIMD fashion. Multiple warps are grouped into thread blocks. A typical size is 1024 or something slightly larger than that these days. These blocks are assigned to a multiprocessor, and it's possible that tens of thousands of threads you might be able to schedule on a multiprocessor at the same time. And multiple such multiprocessors forms the GPU. So this overall, it forms a GPU computation hierarchy, and if we want an optimized graph algorithm, we have to optimize it at different levels in this GPU hierarchy. And since there are large number of these abstraction levels, it becomes a little challenging to optimize your code when we are dealing with specifically graph algorithms. So what are those challenges that come into picture? So warp-based execution is definitely one thing which is going to be very useful for GPUs. However, not always your computation is like that. When we want that the same instruction should be executed, not always the same instruction can be executed when we are dealing with especially graph algorithms. Graph algorithms also require synchronization. That is, different threads might be operating on common vertex, and therefore you might want to lock some data, process it, and then unlock it. This is not always the case in case of, let's say, more regular algorithms. The reason being that at compile time you are able to figure out what threads can operate on what different parts of data. So the locking in case of graph algorithms is really, really expensive when we are dealing with GPUs. The dynamic memory allocation, which might be required for memory allocation of graphs, that becomes costly because dynamic memory allocation requires you to maintain some free list in the either in the kernel or in the user space, but that becomes a sequentiality bottleneck. Also, the caches are very important when we are dealing with regular codes. However, the data cache really does not work well in the context of GPUs because, especially in graph algorithms, because the access pattern is irregular. Plus, there is a limited cache, and the large number of threads, it kind of reduces the amount of memory that is available per thread. And then there are a lot of programmability issues which come up because we are talking about different address space. So you have to copy your data from CPU to GPU, results back from GPU to CPU. Of course, there is some unified space which you can use, but still you will have to model it as part of your computation. There is low recursion support, which is quite, because many graph algorithms, tree algorithms are naturally modeled using recursion. There is a very complex computation hierarchy which we saw, and the memory hierarchy is also exposed to the programmer, which means that the not only the DRAM but also the scratchpad memory, which is the cache, part of the cache, that also is exposed to the user. And imagine your regular CPU code, C code, which you are trying to model, okay, let me put it into this particular place in the cache and so on. So your code, which is probably originally your algorithm might be just 20 lines of textbook algorithm, but if you want to optimize it across all of this, your algorithm might turn out to be maybe 500 to 1000 lines of code. Right? So that adds a lot of challenge while dealing with the GPUs. Right? So I'll skip this part, which is very similar to this, but the last part, the last two parts, the thread divergence and uncoalesced memory accesses, these are kind of very important from the perspective of graph algorithms, because we expect that threads do not diverge, right? All the threads inside a warp, they should execute the same instruction, otherwise they sit idle. They cannot, two threads in a warp cannot execute two different instructions. So the work done per node, since different threads are operating on different vertices and different vertices have arbitrary connectivity, it's possible, the way we were talking about load imbalance, that can lead to thread divergence. So one thread finishes faster, another is still waiting for it to and therefore it is waiting for the another thread to finish it. The uncoalesced memory accesses is like if you have access, different threads in a warp are accessing 32 words in a contiguous manner, then the hardware can combine all these requests, perform a single memory operation, and get all the data in one chunk. This requires that the accesses are coalesced. When we write for I equal to 0, I less than n, and so on, in a CPU, in a matrix-based formulation, it becomes very easy because the data is also kept in memory in that manner. But as we were discussing, node 0 in a graph might be connected to node 60, which are actually separated by a large distance, and therefore coalescing becomes an issue when we are dealing with graph algorithms. So let's first represent the graph in the memory of, let's say, CPU or GPU. Right? So there are two ways that we usually represent a graph. One is adjacency matrix, which is a V cross V representation of the matrix, and each entry ij denotes that the edge ij is present. So node I is connected, directly connected to node j. That is what we say when we are dealing with that entry. This information is quite useful when we are dealing with large graphs, right? So, which means large dense graphs, because most of the entries in this matrix will be non-zeros. However, finding the neighborhood of a vertex becomes order V operation, right? Which means that I have to go through all the vertices to find out what neighbors a vertex is connected to, right? So that looks like this representation, and this is definitely well known to us. The second, which is the list-based representation called adjacency list, so V plus E representation, where E is the number of edges in the graph. So each vertex maintains the explicit list of neighbors that it is directly connected to, which is quite useful for sparse graphs, because most of the entries in the graph, if those are zeros, I might want to use this information, and therefore finding the neighbors becomes order of the length of this chain. One way to think about this is that going back to our school, right, when we used to have a teacher taking attendance. Right? So the teacher would take attendance as roll number 1, roll number 2, roll number 3, like that. That is a dense representation. Now imagine the situation when it rains heavily, and therefore instead of 50 students in the class, only 10 students are present in the class, right? So the teacher is unlikely to use a dense representation. She will say that, okay, tell me your roll number, tell me your roll number, and so on, and accordingly take attendance only for those 10, right? So that is your sparse representation. That's your adjacency list. But these two representations, although quite useful on CPUs, are not well fitted for GPUs. And the reason being that one thing is adjacency matrix, as we have seen, is useful only for dense computation, dense graphs. And many of the graphs that we saw, road networks, social networks, etc., these are sparse networks. Sparse meaning that imagine the number of nodes in the graph, right? So let's say that is a large number, let's say 1 billion, right? How many friends you will have in that social network? Maybe 200, 300, 500, maybe 1000, right? That 1000 number is much smaller than the number of nodes in the graph. And whenever this disconnect happens, you can say that overall the graph is going to be sparse. You can always have celebrities who have very large degree in the graph. For example, let's say Trump or maybe Obama or Modi or some other celebrity, let's say Amitabh Bachchan. All of these people are going to have lots of connections in the social network. However, that doesn't mean that the graph is dense. These particular nodes have large connectivity, but we are talking about the average connectivity, right? So when that connectivity is much smaller compared to the average, the overall number of nodes, that becomes a sparse network. And sparse networks are not, I mean, if you use adjacency matrix, then there are lots of zeros, so you should not be using that. Adjacency list is useful. However, when you have this adjacency list, how do you move that information from CPU to GPU? These graphs are typically stored in a disk, right, in a file. So you are going to read that into CPU memory because GPUs, well, in a standard manner do not currently support accessing the file system directly. So you'll have to load information from the CPU, load it into the CPU memory, and move this graph into the GPU. Now, when you have these pointers, since these have different address spaces, these pointers on CPU may not make sense onto the GPU. So you have to serialize and deserialize the implementation onto from CPU memory to GPU memory. So is there a way we can avoid this serialization and deserialization and still represent the graph in a manner something similar to the adjacency list or a sparse representation? So those lead to something called as, let's say, COO format, coordinate list format, or edge list format. So what you do is, one way is that we just maintain the pairs of source destination, which means that if a graph representation is like, if the example graph is what is shown on the left top corner, then I just stored 0 to 3, 0 to 4. These are the edges that are present in the graph, right? So that is a sequential representation which I can have to represent the graph. Another way is similar to adjacency list, but what I'm going to do is to concatenate these lists. And instead of using pointers, I'm going to use offsets. So the way it is going to look like is that, so on the, okay, let me try this one. So this particular array is the offset array, which means that this stores the offset of the elements which are present in the second array. The second array is actually talking about the destination vertices. So 3, 4 are the destination nodes of 0's starting address. So it is connected to 0. So 0, the entry here is not talking about the node 0, it is talking about the offset 0 in the second array. Right? So at 0th offset, 3 and 4 exist. At offset 2, 3 and 5 exist, which are the neighbors of node number 1. So this is entry number 1, whose offset is 2 in the second array, which means that node 1 is connected to nodes 3 and 5, which are specified here. Right? And so on. For example, the offset here is 9. So 9th entry in this mentions the destination nodes for the vertex number 5 here. Right? So that is how we represent, and this representation is only offset based. There is no pointer that I am really using here. Although I am showing this as pointer here, that is really an offset, and therefore I can represent this information both in CPU memory and GPU memory. Just push these couple of arrays into from CPU memory to GPU memory, and I get that graph representation in time. So this is quite useful for such data transfer. So let's talk about when we are dealing with the parallelization of these graphs, what happens in the context of graph algorithm. So I might have some processing being done on a particular node, let's say A in this. In that, I'm usually going to process some neighborhood of A. In this case, I might process this blue part, which is nodes B, C, and D. So all of this forms a neighborhood of this node. And there could be multiple threads operating on different vertices. So different threads lead to different neighborhoods in this network. These different neighborhoods, if they do not overlap, right? So for example, neighborhood of A and neighborhood of E, these do not overlap, and therefore I might be able to process these two in parallel. In contrast, the neighborhoods of G and J, they overlap, and therefore I should be careful while processing these two threads in parallel. This neighborhood is dynamically decided, which means that it is not available at compile time. Based on how these are processed, it leads to something called as topology driven versus data driven processing. Right? So the application of a particular computation on an active node is called as an operator. Right? For example, in shortest path, the operator is look at the distance of A, distance of its neighbor, and distance of A plus the edge weight, and update the distance of B depending upon whichever is smaller, the existing distance of B or A plus the edge weight. That defines an operator for shortest paths. You might have a different operator, for example, for computation of page rank, betweenness centrality, minimum spanning tree, etc., different graph algorithm. So that defines our operator. And then there is how that operator is defined, that defines the kind of processing. So topology driven processing means that you are processing all the nodes in all the iterations. Right? Topology driven processing means you are processing all the nodes, all the vertices of this graph in all the iterations. Even if there is some work not to be done at node D, I'll still assign a thread to it, which means that that thread is going to sit idle. So only 4 threads in this network are going to process in this iteration. Maybe in the next iteration, some other nodes get active, and therefore those will get processed in the next iteration. In contrast, data-driven processing keeps track of what are the active vertices. Right? So that, similar to our graph representation, topology-driven processing is like adjacency matrix representation, where everybody is stored, right? Even if only a few neighbors are there, all the neighbors are stored for a particular vertex. Similarly, in topology-driven processing, I am processing all the nodes all the time. In data-driven processing, I am processing only the nodes where work needs to be done, which means that these are active nodes. So I am going to process only A, E, G, and J. I am going to store only these, and only 4 threads are going to be launched while processing in the current iteration. In the next iteration, I need to change the thread configuration. So this leads to data-driven and topology-driven, and both of these are useful in different contexts. Many algorithms are implemented using topology-driven processing. When I am dealing with data-driven processing, since I need to keep track of what nodes are active, I need to maintain some sort of a list or a work list for maintaining this information about the active nodes. So overall, we see that the data-driven processing is definitely work efficient because you are processing only the active nodes, whereas topology-driven processing performs some extra work. I need to use a centralized work list, whereas there are no work lists in topology-driven. I need to worry about fine-grained synchronization while dealing with this work list when I'm talking about data-driven processing in case of, so therefore there is a fine-grained synchronization required. By the way, is the audience aware of the atomics on GPUs? Any idea?
Yes.
Okay, great. So those atomics are the ones that are going to be useful for us while performing graph algorithms, because I'll be using some of that in my next slides. Whereas in case of topology-driven implementation, the representation allows us to have coarse-grained synchronization using sort of barriers where all the threads perform operation, then they meet at a particular point, which is called as a barrier, and then all of them process further. Data-driven processing, which requires us to keep track of the work list, etc., it complicates the implementation a little, whereas topology-driven is typically easier to implement. Right? So that is also an important point while dealing with this. The overall algorithm of a data-driven processing looks like this, where I read the input, I transfer the input from CPU to GPU, I initialize the kernel, I initialize the elements, so that is initialization kernel which occurs on GPU. Then I initialize the work list, which means that, for example, for shortest path algorithm, I might have to push the source node into the work list. So that becomes the initialization. Initialize kernel is setting all the vertices distances to, let's say, infinity, right, in case of shortest path. And then there are two work lists which I'm using here instead of one, which is the WL in work list for reading, and work list out, which which keeps track of the active vertices for the next iteration. So while that input work list is not empty, I'm going to apply the operator, right? Get the output into WL out, and then transfer that. So all of this operator processing is happening on the GPU, and transfer that WL out's size, not the complete list, only the size, to the CPU. I clear the input work list, and then I swap the two. Instead of copying WL out to WL in, I'm going to just swap the pointers, and then I go back into the processing, and until that work list becomes empty, I process this. And finally, I transfer results from GPU to CPU, right? So that becomes our data-driven processing. This particular part needs to be repeatedly done. That is our kernel, right? So this, that operator becomes the kernel. This processing is what we need to usually optimize on. So let me show that one particular processing of kernel into this in a more like pseudocode format, but CUDA code is very similar to this. So depending upon the thread which is operating on that shortest path algorithm, shortest path vertex, I consider the source, right, based on WL in of, let's say, thread ID x.x, the distance of that source vertex I get, and then for all the edges, outgoing edges, now that for all needs to be implemented depending upon what representation you are using, either CO format, CSR format, or if you are using adjacency matrix format and so on. So for this particular edge source destination weight, I find out the distance of the destination node, and I calculate the alternate distance of the destination, which is the destination source distance, source vertices distance plus the edge weight. If the alternate distance is less than the destination node's distance, then I update the distance of the destination node, and I push the destination node into the work list, because now that destination node becomes active when I change its distance. Right? So this is the kind of processing that you will do inside a kernel, either using a single global function, or maybe the global function is calling device functions, etc. So the processing starts with that WL in. Threads operate on the WL in different elements, and they create WL out, which might be smaller or larger compared to the WL in. So this processing is the overall data-driven processing, and this is the base version, let's say. Now we have to optimize this processing for a scalability purpose. So let's look at some of the aspects that we will use for optimizing our data-driven implementation. So for example, one of the ways we said is the exposed memory hierarchy. So there is an on-chip cache which is available on the GPU, which I can use for exploiting. So global memory is a big problem, especially for graph computations, because the access latency is much higher. So you would like everything to be available onto the chip as much as possible. So there is a small amount of cache which is available inside a thread block, let's say 48 KB or 64 KB and so on. So that much memory, is it going to be sufficient for us to do something useful when we have large number of threads? So one way of dealing with that is that we can maintain a local work list inside a thread block in the on-chip cache. So there is a global work list WL. I copy that into the local work list, process it, and then use WL out to store the information there. Now one might wonder that, well, how is that going to be helpful? Because you are just increasing the overhead by copying it to WL local and then processing it there, but that doesn't help us in general. Caching is helpful when there is a reuse. So this large cycle here, this means that I am not going to only process the vertices that were assigned originally, but I am also going to process the neighbors of those vertices, and maybe the neighbors of the neighbors, and so on. Depending upon what I set as the threshold, I might process a larger subgraph rather than a particular vertex inside a thread. And that is quite helpful, because I have computed the distance of the destination node now in my previous slide, for example. Let me go back to that previous slide, right? So I have computed the distance of the destination node here right? And I have that information available now. What I need to do is to just use it to process its neighbors. The way the current SSSP operator I am showing on the slide, it updates the distance and then waits for the next iteration of this operator from the CPU to process this particular distance to be pushed into its neighbors. But I can do that right away using this local work list. So that is what I am showing in this particular slide. So that is one way of exploiting the GPU base. So this is very specific to the GPUs, right? So we don't have any access to what kind of information I can push into the cache, but this on the CPU. But on the GPU, definitely I have that luxury, and we should exploit that to get the optimized performance. The another kind of way we can do is that if you look at the amount of work that gets done in graph algorithms, typically the computation work is really small. There are a lot of memory accesses which are happening when I'm trying to access, for example, distance of a source node or distance of a destination node or an edge weight. All of these are stored inside main memory. And when I'm trying to access it, that is going to add latency to my computation. The amount of computation that I do, for example, the algorithm that I showed, is going to be very minimal. I'm going to do one plus operation, and maybe I'm going to do some sort of index offsetting, etc. There is one comparison operation which I'm doing. So the amount of computation is less, the amount of memory access is large. Is it possible that I can improve this ratio? So one of the ways it can be done is that I can have maybe give a sufficiently large amount of work to a thread, right? And if the thread can reuse some of the memory computations, it might be able to do better. One way of doing it is processing the subgraph. Another way of doing it is that I can assign multiple elements to a thread, right? So if the thread launch overhead, although it is minimal, it can add up when we have large number of iterations. So you would like to have multiple chunks of work given to a particular thread, right? So therefore each thread performs operation on multiple vertices rather than a single one. How do you do that? In case of data driven, since the elements are stored inside a work list, I need to extract that information from the work list. So each thread is operating on that shared work list. So I need to synchronize across threads. I can use an atomic to extract out an element from the work list. So if I use one atomic per element to be extracted, I require order of E atomic instructions across different threads. But I can do better because I don't need to really extract one element. I can extract multiple elements out of it. And if I do that, then I can use order of T atomic. So each thread just does a single atomic and gets as much chunk as possible, process it contiguously, and be done with the information, right? So that is order T atomics. Note that order T atomics may not preserve load balance, which might be preserved for atomics per element. And overall, however, when we reduce the number of atomics, the overall synchronization also reduces. There are other ways in which you can perform. For example, you can do without atomics, perform a prefix sum of operations where each thread identifies what chunk of the elements it is going to extract from the work list using some sort of cooperative execution, which is diagrammatically shown here, right? Where there are two threads are operating they are coordinating in parallel and figuring out what is the offset at which it should be extracting information from the work list. So that requires some sort of synchronization after every step, right? So two threads operate, then four threads operate, then n number of threads operate, then n by 2, n by 4, and so on. So you require order of log T barriers for processing this information, right? And depending upon how your what are the sizes of your data elements plus number of elements, one particular mechanism might work better than the other. But it's worth trying out all of these mechanisms. I'll skip work donation, but in detail, but I'll skip briefly mention it. So when we are talking about load imbalance across different threads, one way of dealing with it is that if there is a worker thread which has large amount of work to be done, that is, it's operating on a vertex and that vertex has large out degree. Let's say Amitabh Bachchan's vertex, and that is a large out degree for that vertex. So the thread is going to take a large amount of time to process all the neighbors. What it can do is that it can say that since I'm going to process a large chunk of data, I'm going to probably process only a subset of it, and I'll keep some chunk for other threads to be donated to, right? So then other threads, if they become free earlier, then they are going to have time to process this donated work, right? For example, the other thread might be operating on, let's say, an IIT faculty member, right? IIT faculty member is likely to have very small number of connections compared to Amitabh Bachchan, and therefore let the thread which is operating on an IIT faculty member is going to extract the work from the other thread and process it. So that donation kernel can be nicely modeled, may not be across the whole GPU, it can be done that way, but it becomes little efficient if we can model it inside a thread block, because you have nice sync threads barrier which is available for you inside the thread block. So I create a shared memory for inside a thread block as the donation box. Each thread determines whether it should donate. For it to figure out, it needs to know the average load per thread. So different threads communicate with each other to figure out what is the total average and the number of threads. And that I can figure out the average thread based on the average load. Based on the average load, if my work assigned to me is going to be much larger than the average load, then I am going to decide to donate. That means that I am going to push elements into the donation box, and then the operators are going to start executing on these, and once a particular thread finishes, it is going to look at the donation box. If it is not empty, then it's going to extract information from it. Right? So that is going to be the emptying of the donation box after the actual operator corresponding to the work is done. Right? And we require a couple of barriers to make sure that the processing is in sync. So that requires sync threads at appropriate places. So it definitely improves workload imbalance, and if implemented properly, that is, we have implemented at the thread block level rather than across the GPU, that can definitely improve because your shared memory is fast cache. The barriers are also fast, and therefore this processing of donation turns out to be quick. Yet another aspect which comes into picture when we are dealing with large graphs, which might require a large number of iterations, is to check if you require different configuration of the kernel when we are launching the different threads. For example, in many graph algorithms, the processing is not uniform across all iterations. It kind of increases in the initial iteration and then tapers off and remains low for a large number of iterations. This kind of behavior is quite common in graph algorithms, and therefore it doesn't make sense to have number of threads launched which is probably equal to the maximum of whatever is possible, right? So that is not really very useful, because then you can reduce the kernel launch overhead, which is low, but it can be improved. So we vary the configuration based on the amount of parallelism that is available. And how do you know what is the amount of parallelism that you require? Well, you have the input worklist size in the context of data driven. That size is going to give you how much work needs to be done, and therefore that can be exploited for improving the work efficiency. In this particular plot, I am taking one particular graph algorithm called Dillon image refinement, whose parallelism profile I am showing, but many algorithms exhibit quite similar parallelism profile. Right? So understanding this parallelism profile is an kind of offline activity. You can do that in data-driven processing very easily, but in case of topology-driven processing, this becomes a little challenging, because then you are processing all the nodes all the time. So therefore, you have to be careful, but you should definitely know this parallelism profile, which might be flat for a regular computation. Right? In all iterations, you are doing almost the same amount of work, whereas in case of irregular codes such as graph algorithms, this is going to be a challenge. So let's come back from data-driven to topology-driven. Topology-driven processing, as we discussed, it's going to operate on, it's not going to maintain any worklist. We are going to launch number of threads equal to probably number of graph elements, which could be number of vertices, which could be number of edges, etc., which could be in millions, by the way. So we again read the input, transfer the input to the GPU, initialization kernel, and then again there is a do-while loop which is going to perform an operation, and there is a flag which we need to maintain, which checks if I require another operation, another iteration or not. So that processing I am showing here, where all the nodes are considered to be active, and therefore all the threads operate on them. And to make sure that we terminate, we need to maintain some sort of a flag that whether work needs to be done or not. Even if there is work needs to be done at one node, we have to again do this processing, another round of this operator needs to be executed. So this becomes our base version. Let's see what kind of optimizations we can do to perform a better topology driven implementation. So the first aspect which comes in is kernel unrolling. Right? So instead of operating on a particular, like we were discussing in data driven also, instead of operating on a particular node, I operate on a subgraph. Right? So if you look at this, as I was mentioning, there is also a memory bound kernel, which means that there is little computation, plus, less than, offset computation, etc. And there are multiple memory requests which are happening, which are uncoalesced by the way. So I can increase the amount of computation by using kernel unrolling. So what I do is that instead of operating on a particular node, active node, I operate on this particular neighborhood. So I make all of these as active nodes, and one thread operates on each of these active nodes. Right? So then one question that comes up is that how about this thread? Wasn't this thread, because of topology driven processing, operated on by some other thread? Yes, that is possible, which means that the same thread here, which is assigned here, is updating some information here, possible, or the thread which is operating on this one is also updating the same node's information. So there is a possibility of a conflict which can come in, and therefore this particular statement needs to be protected. It cannot be arbitrarily written like this. This is a pseudocode, more in sequential form, but this needs to be protected using an atomic min operation. Right? So this kernel unrolling, which is quite similar to loop unrolling as we know from the CPU domain, but this is not similar to loop unrolling. Loop unrolling is probably, I would say, similar to work chunking that we saw. In this case, the hierarchy or the neighborhood also comes into picture. The structure of the graph is important. So it should not be the case that a particular thread which is operating on this node starts processing this node. The information should also get propagated. So this information is available for this node, right? When a thread is operating on this one, and therefore it makes sense to perform operations in this neighborhood rather than some arbitrary node. Right? So that improves the overall processing in this, and the information also propagates faster because you are not waiting for another iteration to happen, right? Another round of processing to happen, another operator to be invoked, and therefore the processing is faster within the graph. Any questions here?
Race condition kind of thing, or if we maintain it as an atomic operation on pushing on the stack, then won't there be some serialism across all the threads?
Yeah, that's a good question, good observation as well. So this is, I would not call it as a stack. This work list is more implemented as a large array, right? And then this large array, since everybody, there is a shared global entity which is being operated by different threads. They are reading as well as writing to the same array, and therefore, as our friend rightly pointed out, it requires synchronization across threads, right? This synchronization can be done either by using atomic instructions, right? That is one good way of doing. Or you can use prefix sum to decide how many, depending upon how many elements you want to push, you can decide the offset at which you are operating and then push the elements in parallel into that work list. Right? So very similar to what we saw in the work chunking, where there are single atomic per thread versus multiple atomics per thread versus prefix sum. This is very similar to that operation. So the question, again, I'll just push it further, that isn't it possible that this additional overhead outweighs the benefits of data-driven processing? It can. In general, it doesn't when the graph is sparse and the size of the work list is small. Right? So the graph size is large, but the amount of processing that you do in every iteration is small. In that case, this synchronization overhead that you have, it kind of gets offset by the benefit that you get by processing only a minimal amount of work. All right, so let's, I'm sorry about that. Okay, so this is what we processed. The next optimization that we can apply when we have topology-driven processing is to take advantage of the memory hierarchy again, and it relates to the kernel unrolling that we saw on the previous slide. So depending upon how much neighborhood I want to process, I decide what is known as an unroll factor. which means that I might decide to process only the immediate neighbors or neighbors of neighbors or 3-level neighbors and so on. That gives me how I am going to operate a subgraph. This subgraph I can process in different ways. For example, I can process it in a BFS manner or a DFS manner, and it turns out that for different algorithms, different strategies are helpful, right? Although the difference is small, it actually can give some benefit and it accumulates if the number of iterations is large. If you are using a BFS on this subgraph, you require a queue. If you are using a DFS, you require a stack. Where do you store this information? Since that kernel unrolling is being done inside the thread block, you can use a thread block's shared memory to process this, to store this information inside a queue. How many elements will be there in the queue? Well, this processing is happening per thread. The thread block, the shared memory is shared across all the threads inside a thread block, let's say 1024 or something. Assuming that there are 48k byte memory which is being used for the shared memory and 1024 threads per thread block, you have approximately 12 integers or 12 words available for each thread. This particular 12 element queue or stack can be used for each thread for processing the neighborhood. And depending upon that size, you might want to decide whether you want to go to single neighborhood or double neighborhood or 3-level neighborhood and so on, right? So that size of the queue is actually decided by the unroll factor. But I would say that how much memory is available, because not always you will launch the kernel with 1024 threads per thread block. You might have lesser number of threads per thread block, in which case your queue size can increase and therefore your unroll factor can increase, right? So that can give you some benefit versus inefficiency trade-off. So that is again exploiting the memory hierarchy in a topology-driven setting. It definitely overall reduces the memory latency, but it requires careful selection of the unroll factor. Let's go back to our issue of that node 0 is connected to node 62, right? This is a very arbitrary connectivity. Is it possible that I reorganize the graph such that nodes which are connected logically, right? So node 0 is connected to node 62. Is it possible that I can also connect them or push them together or push them close by in the physical world also? So what I can do is I can renumber the nodes, where node, let's say node 1 is specified as, so this 45 node number is specified as node 1, right? So I renumber the graph such that the node numbering gives us the neighborhood, the nodes which are numbered nearby are also nearby in the actual memory when I load the graph into it. And in that case, both the coalescing as well as some sort of caching can also help us in improving the overall performance. So that can help us in overall throughput improvement of the algorithm. All right, so these were a few aspects, and I'm going to continue a few more before we look at some of the numbers. So one of the ways in which we said that there is an atomic instruction might be required for processing is that when I'm operating on a particular node, let's say thread A, vertex A, I might push the information, propagate this information to an adjacent node, let's say here, right? However, this particular node might also be the destination node of some other vertex. In that case, two threads are writing to the same memory location. There is a possibility, and therefore we need to worry about synchronization. This kind of processing, where the information is propagated from one neighbor to its outgoing neighbor, is called as a push-based implementation. I can think about a pull-based implementation where a thread is operating on a node A, and what it does is, instead of pushing the information to its out neighbors, it pulls the information from its in neighbors. The advantage of this pull-based implementation is that now I can guarantee that each vertex is being operated or being written to by exactly one thread. And if that is the case, I can avoid the use of atomics while updating the information. Let's say in this case, shortest path distance I am updating. That can be quite beneficial in some algorithms. However, we have to be careful while dealing with this, because if you recall our adjacency list representation or a compressed pass row based representation, it is outgoing neighbors implementation, right? So we maintain the one array which is the source vertex, and then the adjacency list is talking about the destination vertex. So it is, you can go from one neighbor to its outgoing neighbors. I cannot go from a one particular vertex to its incoming neighbors. So if you want to use a pull based processing, either you have to change your implementation, graph representation, to use either CSR or the adjacency list representation, but I have to change the source destination representation. So for each destination, I am talking about I am storing the source nodes corresponding to that. Then pull based implementation can be implemented, right? So that we should be careful about. So your optimizations might depend upon the graph representation. Similarly, there exists frameworks which store the graph in both the incoming neighbors format as well as outgoing neighbors format, and then you can possibly apply both the optimizations. When we are dealing with push based implementation, let's talk about the issue that comes up even while when I am not using atomics, right? So let's say that there is a node which is having a current distance of 10. I'm talking about, let's say, shortest path algorithm, right? If I am not using any atomics, right, and there is another thread which wants to write information from, so T5, it wants to update the distance from 10 to 5. And there is another thread T7 which wants to update this information from 10 to 7. If things happen correctly, well, T7 might execute first, it will update it to 7, and T5 might execute later, and it will execute update from 7 to 5, and the distance update is correct because we are interested in the shortest distance. But if the execution order is different, which can happen depending upon the scheduler, T5 might go first, it will update from 10 to 5, and when T7 tries to update, it might overwrite that 5's information to 7, right, if we do not use any atomic instructions. And therefore, we can get a lost update. This is called as a lost update problem. Although I took the example of only shortest path, this can occur in other algorithms as well. However, in case of data-driven processing, we can use atomic instructions and get rid of this problem. So in this case, we'll use atomic min instruction of that is supported by CUDA, for example. However, if you are using a topology-driven implementation, right? So let's again look at this problem that your update of 5 was overwritten by update of 7. However, in topology-driven implementation, all the nodes are active all the time, and therefore these T5 and T7 are going to be active again in the next iteration, and therefore in the next iteration you will still update from T5 the value of 7 to 5. So topology-driven implementation allows us to exploit this monotonic update property of distance computation in shortest path algorithm to avoid the atomics and still be able to get the correct answer. So these are exploiting certain properties of the computation to implement such an implementation. Similar thing will happen in BFS, but then there are better ways in which you can implement BFS, for example, level by level, instead of going for such a mechanism. So what the point here is that you might want to change the processing in a different way for a graph-based algorithm, but sometimes you might also want to exploit certain properties of the graph algorithm computation itself to improve the synchronization. Right? There are several graph algorithms which, for example, when we tried to implement those in our group, we got sufficiently large speed up compared to sequential CPU implementation. And I'm sure you will be able to do that when you implement all these optimizations. Okay, a quick question. Identify this celebrity. So anybody wants to come to the mic and answer?
I'm guessing it's Arnold Schwarzenegger's face in George Bush's photo.
Good one. Okay, so that is that was a good one. This one is something called as a morphing in graphics applications. So although I am not going to talk about this interesting application. What I'm going to talk about is a little bit about morph algorithms. So what we mean by morph algorithms is when the graph structure itself changes. So far what we discussed was more about the graph structure remains fixed and there is some computation which you are performing on the graph. So information is propagating across the graph. What I am now talking about is that the graph structure itself is changing. Right? So it's a dynamic graph algorithm or a morph algorithm. Right? Do we know any examples of morph algorithms that occur in practice? Well, there are lots. For example, the Delaunay mesh refinement that I talked about, where you are given a mesh and then there is a triangulation of this mesh. So different points in this mesh are connected to form a triangulation. And this triangulation needs to be reformulated. For example, if I look at this particular part, I might want to remodify it to fit such a structure. So that is a update of the mesh structure, right? So that gives rise to a dynamic or a morph algorithm. Similarly, this particular set of statements is talking about pointers and various addresses. I can model it as well as a graph problem and updation of information. For example, there is flow of information from B to star P, where P is actually pointing to A, right? So there is information flow from B to A, and then there is another information flow from A to C because of this statement. So that can also be modeled as a graph problem, which is from compilers. Then I can talk about survey propagation. Survey propagation is actually something which deals with identifying how, let's say, epidemic spreads in a network, or how rumor spreads in a network, etc. But interestingly, it gets used for solving SAT problems. So the CIs, the blue boxes, are constraints. For example, in a 3-SAT formula, you will have these constraints, and then each constraint is associated with certain variables. And the dotted lines indicate that those are negated variables. So you can represent a SAT formula using a graph algorithms and seed them with certain values and propagate them and perform some computation to figure out whether the formula is probabilistically satisfiable or not. Right? So that algorithm is called as a survey propagation. Right? So and then of course more classical graph algorithms such as minimum spanning tree, shortest paths, etc. So you can see that there are large domains from where graph algorithms come into picture. Once you model them as graphs, then all our graph primitives, all the processing that we have studied so far, all of that becomes very useful for processing all these graphs. So how do you deal with such graph algorithms, morph algorithms? So some of the challenges that occur when we are dealing with morph algorithms is synchronization again. We have to, now since the structure itself is changing, so far we said that the graph is static, so I could just process it arbitrarily, but now the graph structure might change. When I'm operating on a particular vertex, that vertex might disappear from other thread, or when an edge weight is being looked at, that edge weight might change by some other thread. So I might want to use something similar to what we have done in CPUs, for example, logical locks. But locks turn out to be quite expensive on GPU, so we have to deal with, or we have to innovate new protocols to deal with such synchronization efficiently on the GPU, especially by exploiting the memory hierarchy, computation hierarchy, by taking into account, let's say, various barrier instructions available. Can we reduce the amount of synchronization accordingly, etc. The memory allocation becomes a challenge because so far it was static, now suddenly it becomes dynamic. And if I have to allocate memory on the GPU, I can use malloc on the GPU. There is some heap available on the GPU, so you can use malloc on GPU. But malloc, as we discussed, has to maintain a free list, and therefore it is currently a little slow. And therefore it becomes a kind of scalability bottleneck. The other option is use CUDA malloc on the CPU, but for that I have to transfer this information, how much memory we need, to the CPU, allocate the memory there, and then get it back onto the GPU, right? So this can create efficiency bottlenecks. Load imbalance is not only now different across different threads, but it also goes on changing as the algorithm progresses, because the graph structure is changing. Earlier, whatever had less number of edges, outgoing edges, now might have large number of edges, and so on. So all of these aspects make the complications much, much bigger. So if at all you are interested in more challenging problems, you should definitely work with dynamic graph algorithms, right? there are lots of different aspects which we have come up with in the context of not only we but several other groups in the world, which can be nicely grouped into computation related optimizations, memory related, and the synchronization related aspects. For example, in case of synchronization, I might decide to avoid the synchronization altogether. What are the situations in which you will be able to do that? Or I might want to coarsen the synchronization, where instead of using atomics, I might want to use barriers. Right? And then there are other mechanisms which I will not get into. In case of memory related operations, we looked at, for example, kernel transformations such as kernel unrolling. I can group data items together, for example, work chunking. I can exploit the memory hierarchy to take advantage of on-chip shared cache, etc. In case of computation, well, the first thing that comes in is that which algorithm you are using. You have to choose a proper algorithm to make sure that it fits well onto the GPU regime. For example, on CPU, it's likely that you will use Dijkstra's algorithm for shortest path. But on GPU, actually it is not, or even on CPU in parallel, it's not the best algorithm to go for because it has limited parallelism. Right? You are using a priority queue where you are extracting only the min at every time. To maintain the properties that Dijkstra gives, that whatever you have relaxed so far, that is the optimal distance. That is not possible if you change from heap to something else, right? So you might want to relax that constraint, but increase the amount of parallelism so that the overall processing still takes lesser amount of time. For example, Bellman-Ford's algorithm turns out to be a better fit for massive multi-threading based on processing such as GPUs. I can sort the work, which improves the thread divergence, but then sorting itself has n-log n complexity. But is there a way I can do better? Well, I don't really need a full sort. I just need some sort of bucket sort. I can do that in a single linear pass over the input. But I might have to do it dynamically as the work changes. Work chunking we saw, computation and communication overlap. So while one kernel is executing, let me use the PCI Express bus to keep the data ready for the next iteration so that I don't have to wait for the next iteration to happen. Right? So that overlap of computation and communication is another classic way of improving this parallelism. And I need to follow the parallelism profile, and I should do pipeline computation, etc. So all of these are various optimization principles. And what we have found out, and others have also found out, is that these are critical for high performing irregular computations. What this means is that if you want a high performance, you cannot avoid doing this optimization. It won't be the case that you take a textbook graph algorithm or a highly optimized CPU implementation, port it onto the GPU, and it will suddenly give a high performance. That is unlikely to happen. You have to spend time in improving your GPU computation for taking advantage of the GPU specific aspects. I'll briefly talk about the approximations. There were two aspects which we talked about. Since I have, I think, around 7 minutes, I just spent some time on the approximations. We talked about two ways in which large graphs can be modeled or can be their processing can be scaled. One was storage related, another was time related. And within time, we talked about parallelism, and another was approximation. So I'll just spend one slide on this one. For example, I can perform approximations in various aspects. Not always I want the exact answer. Not always I'm interested in exact shortest path. It doesn't matter, for example, if you are going from IIT to, let's say, IIT Kanpur train station, right? I'm not so much bothered about whether distance is 10 kilometer or 11 kilometer. Right? That approximation is still helpful for me. When you are, for example, booking Ola, it gives you some estimate. That estimate can be off by, let's say, 10 rupees, 20 rupees. It is still okay. Right? So we do have applications where such approximations are useful. So there are simple techniques which you can use for approximating, which can help you find a quick answer. It's also possible that you might find an approximate answer first and refine the answer later. For example, the way, JPG images get loaded in a browser. First you see a blurred image, and then suddenly different parts of the image get cleaner, right? That is how the JPG format is. There are two, it's a hierarchical representation. There is a blurred representation, there's a smaller approximate representation, followed by the later one. Right? So similar things we can apply to the computation as well, and more so when we are dealing with large graphs. So I can reduce the computation, which means that I can just reduce the amount of processing I am doing, which means I can reduce the number of iterations that I am performing, and I might get an approximate answer. Right? That might suffice for graph algorithms because as we saw, the parallelism profile, it performs more chunk of work initially. So the later part I can always do away with if I am okay with approximate answer. This might be difficult to do when you have a flat parallelism profile. Similarly, partial graph processing. So I need not process all the graph all the time. I can process fewer number of edges or fewer number of elements, right? I can perform graph compaction. If it is lossless, then I don't get any approximation. But if it is lossy, then I can get into some approximation. For example, if two nodes have the same neighborhood, I can represent them together as a single node, get the processing done, and then say that both of them have the same attributes. Alternatively, if two nodes have almost the same neighborhood, how will I find that out? Well, I can, for example, take a Jacob's coefficient similarity between two nodes' neighborhoods, and if the coefficient is, let's say, above 0.8 or something, which means 80% of the nodes are common, I can say that these two nodes are the same, merge them, in which case I'll get an approximate answer corresponding to this when I run the exact algorithm. Similarly, I can approximate the attribute values. I mean, instead of saying that these attribute values could be arbitrary, I can just say that these are always going to be powers of 2, for example, or multiples of 10 and so on. So then I can approximate these values to get less distinct values. And if you have less distinct values, you might require lesser storage for representing. And there could be more which we can devise based on your approximations. Right? So if you look at more in an algebraic sense, you can have an approximation A which goes from domain D to some, and you can apply some function f. That function f operates on an entity and gives another entity, and both belong, the entity belongs to the domain, right? So for example, an attribute value or an iteration and so on. So for example, an iteration, the way I can put it is that any greater than k iteration, I map it to a iteration k, right? So that becomes an approximation, and similarly others you can put in a similar context. Finally, I'll just take a couple of minutes to talk about our group. So all of these processing and many more have been part of our group. Our group is called as Gajendra Group, and lots of different aspects we work on. But definitely graph algorithms is at the center theme. So synchronization, energy aspects in graph algorithms, approximations, graph DSL, clustering, all of these are kind of related to graph algorithms. There are other offshoots which students are always interested in, for example, testing and Android. Although we always try to map it back to graphs. For example, in testing also you can deal with control flow graphs and mapping between test cases and different basic blocks, etc. So we try to come up with sort of graph algorithms for them and processing them in parallel. And there have been a lot of appreciation that we have received in the past, which I'm just mentioning it here. So finally, I would like to thank again Preeti and Ashish sir for inviting me to this. And if there are any questions, we can take those up now.
Hello, sir.
Yeah, go ahead.
Sir, so now we had seen that you had explained that if a serial algorithm cannot be directly implemented on GPU, and we cannot expect a good speed up. So what about parallel algorithms on multi-core? Like if someone has written a multi-core algorithm, if we directly implement that on GPU, and if we get a speed up, is that a good claim that we have done this on GPU? And can we claim that it's something our work?
Well, if you are talking about research, it might be a little tricky. These days it so happens that, the days are gone when we can implement one particular algorithm on the GPU and I could publish that, right, in a reasonable venue. Right? So that no longer exists. What you will have to show is some common principles via multiple algorithms, right? So those are going to be interesting ones for the community. Talking about if there is already a parallel algorithm existing on CPU and you do it on the GPU, that is still possible, but you have to make sure that you are able to show enough non-triviality in that parallel, in that translation. If you are able to show that it is interesting, I think it's still publishable.
One more question. So if we want to compare the speed ups now if there is some problem X, on that we are getting some speed up using multi-core, and I am getting some speed up using GPUs with different algorithms. Right. So is it fair to compare with the multi-core, like, because GPUs I think that GPUs are more powerful, then if GPU gets 40x speed up and if the multi-core version gets some 5x speed up, can we tell that the GPU algorithm is better than the multi-core one?
Yeah, so this question often comes up, and if you are a research scholar, your committee member who might not be from the parallelization domain might ask you this question in your defense or final presentation, that is it fair to compare between CPU and GPU, or GPU has these many cores, is it fair to compare, and so on. So typically a person who is working in parallelization may not ask you this question. The reason being that yes, these are different architectures and it's difficult to compare across these architectures. That is for sure. However, there is no easy baseline in the sense that you cannot, you can always put that I am getting this performance per core, per gigahertz or something, right? Because the frequencies of CPUs and GPUs are very different. GPUs might have much lesser, maybe 1/3 of the frequency of what the CPU might be clocking at. So that way also it's not fair, but we cannot always say that GPUs are going to perform better. If you have a lot of sequential component in your processing, CPU is likely to be performing better, and you should actually use CPU for that processing. You need not always run GPU, or different parts of the algorithm, if those have sequential components, it's better to run those parts on the CPU. The comparison is not, it's difficult to argue. I really cannot say that you will be able to argue that, but the one thing that you can help with is talk about performance per core, per gigahertz, or per watt, whatever is the more appropriate in your setting. Those might be kind of reasonable numbers to compare across. And you can always put in this that I attended one HPC workshop at IIT Kanpur, and there one faculty member from IIT Madras said that this is okay, so I am comparing it that way. So many papers actually compare against the CPU speed up to GPU speed up. So that is quite widely accepted notion. Right? So you can always cite many papers from, for example, PPOP, IPDPS, HIPC, etc., which will be able to allow you to compare in this manner.
Thank you, sir.
Sure.
You mentioned something about dynamic graph theory. Can you mention similarly anything state of the art from the graph theory which is happening right now?
In fact, the two aspects that I mentioned, the dynamic graph algorithms as well as the approximations, these two are definitely at the forefront of current research in graph algorithms. One of the interesting aspects that come up there is that you have good theoretical algorithms from graph theory, which are available for dynamic graph algorithm. For example, maintaining connectivity across two nodes when the graph structure is changing. This is available in the theoretical setting. When you try to implement that algorithm on the GPU or even on the CPU, you might require a large amount of time to implement that. Plus, performance is going to be going for a toss. The reason being that theory people will always say, my wife is a theoretician, but so she will always say that, the constants are large, right? So therefore it's possible that you might not get good performance out of this in the parallel setting or even in the sequential setting. But how to remodel the computation, keeping the algorithm the same, but some parts of it, can we model it such that it suits, let's say, the GPU architecture? Those are still challenging. And although we have higher level information about how the algorithm should be working, we really don't know if there are common principles which apply to a multitude of graph algorithms. So definitely those issues are open, and you should definitely apply those things. Another aspect which is coming up is, for example, many of you would be interested in machine learning, deep learning aspects. Many of those algorithms are actually embedded as graph algorithms. And for example, your neural network is a graph. Right? So when you are propagating information across neural network, you can optimize those libraries on the GPU or even on the CPU. Of course, some implementations do exist, but I think there is large amount of work which is getting done in the intelligent systems domain, and modeling that efficiently on the GPU is definitely something which our HPC people need to come forward and apply.
Rupesh, I think there are no more questions. And you have been thanking us. In fact, we should be thanking you. So I just wanted to make that point, should not be missed. So it was a really nice lecture. And I think your absence was not really felt.
Thank you.
Okay, so shall we disconnect? Huh? Preeti, you want to make some?
Thank you so much, Rupesh, for taking this effort of connecting over Skype and
Yeah, I'm sorry again about this one, but yeah, let's hope it all is fine. I'll share the slides. You can
yeah,
possibly
please
share
send
it.
the slides. I'll
I'll
upload to
share.
the website. Thanks
Sure,
again.
thanks a lot. All right, bye guys.